Okay, this is my first private Zoom meeting that I'm trying in order to share with you some information on how to do learning assignment number 4. I received a couple of emails, and normally we do this on the board in class, and I just wanted to make sure that I shared some helpful information with you. So on the right-hand side of my screen, you see that I have the learning assignment open. And then here on the left side of the screen, I have a periodic table that looks a little different. And that's because it not only shows the small atomic numbers in the left-hand corner, but then these values down below each symbol are not the atomic mass, they are the electronegativity value. And when I post this video, I'm also going to give you a link to a Bozeman science video about covalent bonds. And partway through the video, he talks about how electronegativity works. And just in general, do you see how we go from dark green to yellow to orange and then up here in the red on this chart? And basically, if you look here, green is low, and then moving to the right, it becomes increasingly warm, and then red, it says high. And the reason this is an electronegativity periodic table is that the ones that are the red have the most electronegativity, and the ones that are the green have the least. And then as you can see, the ones that are just white background, there's no data for that. And electronegativity, if I scroll down here and I highlight, I'm just going to read this off. It says electronegativity is a measure of how easily an atom attracts a pair of electrons to form a chemical bond. A high electronegativity value means an atom readily attracts electrons to form a chemical bond with another atom. A low electronegativity value means an atom readily donates electrons to form a bond or is electropositive. So basically, if you think about this, these guys over here on the right that are very high are warm, and these guys that are over here on the left, they're going to have the greatest electronegativity differences. And actually, that means they're the most likely to form ionic bonds, because these green guys are going to give up one or more electrons, and these guys over here that are orange and red are going to receive or accept electrons. But when we get to where we have some of the intermediates and the red, that orange and reds, then it becomes a little trickier. Are they actually giving up electrons, or are they sharing them? And if those electrons are being shared, are they being shared equally, or are they being shared unequally? And that gets at the question of polar versus non-polar covalent bonds. And if you look over here on the green side, hydrogen, it's interesting to note, has an electronegativity that is much more like these yellows over here farther to the right. And that's because hydrogen just has one proton and one electron, and it has a single valence shell. And so that one proton in the nucleus is very close to the single electron. And so hydrogen's nucleus has a high affinity or attraction for the lone electron. And so hydrogen itself is, very unlikely to give up that electron, although it does sometimes. So when you look at this assignment, what are you supposed to do? Well, I'm going to go ahead and fill in a little bit. Based on the periodic table, you're supposed to figure out how many valence electrons. So if I look at hydrogen, it's in column 1. So I know that it has one valence electron. And if it was going to gain or lose any electrons, well, it's in the first row. So how many does it need? It would need to gain one so that it would have a total of 2 and its shell would be full. And then using the table, I can fill in that its electronegativity is 2.2. Then I'll skip down a little bit to nitrogen. I find nitrogen here, and we leave out the middle elements. And if you were at my Zoom meeting the other day, or you watched the video, you would know this is column 1, column 2, 3, 4, and 5. And that means looking at nitrogen, I see it's in column 5 and it's in row 2, so it has 5 valence electrons, and because it's in row 2, it needs to get a total of 3, and it would gain them. So here for hydrogen, I'll put 1+ that it would gain it, or it would need to lose one. And I could say that as 1 minus, right? And then over here, I would say for nitrogen, it needs to gain 3 or it needs to lose 5. And what's its electronegativity? Well, based on this table or chart here, its electronegativity is 3.04. And then let's fill in sodium. So then sodium is Na, and it is in the first column, so it has 1 valence electron. And because it's only in the third row, it needs a total of 7. So it needs to add 7, or it needs to lose 1. And its electronegativity based on the chart is 0.82. So you can see how filling that would work. And then you can go in and you can look up this information about charges, but just think about it. If you lose an electron, then you have more protons than electrons. So what would you have? You would have a positive charge, okay? And then you need to read a little bit more information and learn about ionic versus covalent bonds. And so if you think about it, what is an ionic bond going to do? It's when one atom transfers valence electrons. So that's what I'm typing in, to another atom so that both atoms achieve full valence electron shells. So think sodium chloride. The sodium has 1 valence electron, the chlorine has 7. So sodium will donate or contribute 1 electron group over to chlorine, and it's 7 plus 1 makes 8, and so then it has a full valence shell. So that's when electrons are transferred, and then we have an ionic attraction between those two oppositely charged ions. But here, a covalent bond forms, oh, look at that typo. Covalent bonds form when 2 atoms share electrons such that both atoms have full valence electron shells, some and often all of the time. And so if I were to think about how that would work, if oxygen bonds with oxygen, then I'm going to show that we have O, and I'll use an equal sign, double bonded with another oxygen, and we're going to have actually, and I'm going to put it like this because I can't draw it very well here, but we would have 2 lone pairs, and so we have 2, 4, 6, 8 for this oxygen and 2, 4, 6, 8 for that oxygen, and so those 2 lines represent the double covalent bond. And oxygen, right, they have the same electronegativity, so there's no unequal pulling on the electrons, and so they would be the same. So if I look at this here, hydrogen and hydrogen, well, their electronegativity is equal, right? 2.2 minus 2.2 is 0. So my bond type, I'm going to fill in here, would be nonpolar covalent. And how do I draw the bond? Well, I would draw it like this, a hydrogen single bonded with a hydrogen, right? Or if you wanted to, you could show it like this, with the 2 electrons shared between the hydrogens, okay? And then how would I show hydrogen and nitrogen? Well, let's look at hydrogen is 2.2 from the chart, and nitrogen is 3.04. And so the difference between them is 3.04 minus 2.2, so that is 0.84. And if you look here, it says nonpolar covalent bonds form when the electronegativities of 2 atoms differ by less than 0.5, and polar covalent bonds form when the electronegativities differ by more than 0.5 and less than 2.0. So what would I say about hydrogen and nitrogen? I would say that I'm going to get a polar covalent bond, because the ionic bonds form when the electronegativities differ by more than 2, and clearly that difference is 2. And just to fill it up here with hydrogen, 2.2 minus 2.2 equals 0. So clearly nothing's going to happen there. And then let's look here, sodium and chlorine. Well, sodium is 0.93, and chlorine is 3.16. So the difference of 3.16 minus 0.93 is 2.23, if I'm doing the math in my head right. And so, well, look at that here. Based on the information that we have, it's not less than 2.0. It is more than 2.0. So we're going to say here that we have an ionic bond. Okay, so how would I draw that? We don't draw a bond between these. We draw it like this, NaCl, because what you started out with, if I back up a little bit, you have Na plus, oops, excuse me. You have Na plus and you have Cl minus, the ions, because of the transfer, and then they are attracted to get to each other, so they become sodium chloride like this. And up here with the hydrogen and nitrogen, how would you show that? This is where I'm going to struggle a little bit here, and maybe I'll cheat and I'll show you. And I would show you that, remember, nitrogen has a valence of 5, so I want to show you what NH3 looks like and give you an image. And this is actually the best one right here, or this guy right here. See those two electrons that are the lone pair, and see how nitrogen is going to have 3 spots in its valence shell because it has 5, so it has 3 spots to make a complete valence of 8, and so it's going to have those bonds. And the way I would actually draw that is we should see that the N is slightly negative and that those H's are slightly positive. That particular diagram does not show that. Scroll down a little bit. Nope, I'm not lucky now to show that. And so what I would try to do, you know, obviously copying and pasting probably isn't going to work so good. Let's just for kicks see what happens. It's going to give me something humongous. Yeah, see how that works? So I'm going to tell it, no thanks. And undo that. But you would draw this in that box. Because I'm screen sharing and I don't have my overhead, it's hard for me to draw that for you at this point. So moving down to water chemistry, this is where it's really important for you to watch those videos that I posted yesterday. And so I want you to think here about, what do you know about the water molecule? And hopefully you have watched the Bozeman Science one already. And if I were to look at the water molecule, this guy right here, you can see that there are these 2 bonds right here, and they're covalent, but are they non-polar, polar, or ionic? So I'm going to go for, well, I know that we've got those slightly negative and positive regions, and let's talk about this and why it would be that way. So if we look at the electronegativity chart here, hydrogen is 2.2 and oxygen is 3.44, and the difference is equal to 1.24. So if I scroll back up, you can see that a polar covalent bond forms when it's between 0.5 and 2.0. So oxygen will form a polar covalent bond with each hydrogen. So that's what I'm typing up right here. Okay, so what do I type in here? Each water molecule forms 2 single covalent bonds, and these bonds are non-polar covalent. Okay, now what you need to draw here is this that I just showed you in this diagram. Okay, and then do you remember what it's called when the water molecules attract one another? I'm not going to tell you. You have to have read. And now here, based on the videos that I created for you, I want you to draw what it's like for something that is either ionic or polar to be surrounded by water. And then you need to fill in this table here. and then go through the PowerPoint and the textbook and answer these questions about the properties of water. So why it's a solvent, how it dissolves, how water stabilizes temperature, why ice floats, and down at the bottom, cohesion and adhesion. And I really, for learning about electronegativity, if you want to know a little bit more, the website that I'm going to give you for Bozeman Science is, all I typed in with a URL search was I typed in Bozeman and electronegativity, and I'm going to show you what it gave me. It gave me this one that's called covalent bonding. And if I go forward a little bit, see the chart right here? He's going to talk to you about electronegativity, and then he's going to explain how the nonpolar covalent and the he's going to talk about electronegativity differences and how to decide if it's nonpolar covalent, polar covalent, or ionic. And his values differ just a little bit, but that's okay. Follow what's in the learning assignment, and there is some wiggle room there about the difference between ionic and polar covalent, and to some extent it depends on the size of the atom and how far those electrons are from the nucleus with what's going to happen there. Okay, so the next thing that I wanted to show you, because I forgot to go back and hit record when we started talking about this, was I neglected to go back and record the pertinent part of the video when we talked about the lab yesterday. So I'm going to pull this screen over and open up the lab. And just give you a really, really quick walkthrough here. And if you've done the learning assignment, you should be able to do the lab. And it's of course opening in the other screen. Here we go. Make that bigger for you. Okay, so the first activity, use the periodic table, use what you know about building an atom, and draw a picture of an atom that has 2 protons and 2 neutrons in its nucleus and 2 electrons in orbit. And then you need to think about what that means. Is its valence shell full or not full? And that should help you answer if the atom is stable on its own. Then for this one, looking a little bit familiar, red is oxygen and the white's hydrogen. If you watched my video, you'll definitely be able to label this diagram, and don't forget to explain why there are charges present and why they're partial charges, and basically describe, you know, oxygen's electronegativity. In activity 2, please do watch this YouTube video, and basically this is really important here to think about how water molecules are attracted to other atoms or elements that have a positive or a negative charge, and it may be because they're polar or because they're ionic. And basically what you're going to be doing here is creating hydrogen bonds, and you need something that you can basically charge with static electricity. And so you're going to use something plastic, and you're going to use some soft fabric, or I guess you could rub it with your hair, and you want to make it charged, and then you fill a cup with water, and then as you pour the water into the sink, nice and slow with a little stream, you are going to take that object and move it close to and far away from the little bit of water pouring out. And basically you need to explain why that stream is moving based on what you know about hydrogen bonding. And the video, basically, if you couldn't do this on your own, would simulate that for you, and you should be able to answer the questions. And this hint is important. You're making the plastic rod negatively charged. So think about this water molecule up here, and if the the rod is negatively charged, what part of the water molecule is going to be attracted to those negative charges of the rod or the comb? And so you should draw that appropriately here in this box to show what part of the water molecules are being attracted. And make sure you show in the molecules where there are bonds and what kind of bonds they are. Show the partial charges, show the hydrogen bonds, okay? Activity 3 is just what it says it is. You want 2 ice cubes, 2 little containers. The ice cubes should be close to the same size. It really doesn't matter what kind of salt you use, just use, you know, a teaspoon or 2, right? It says cover the ice cube in the salt beaker with full but light coat of salt. So like I said, a teaspoon or 2. And then basically you need to predict, you know, state ahead of time, what do you think will happen? Will the ice melt in both those little cups at the same rate, or will one be faster? And why do you think it's going to be faster? And then basically just get it going and look at them periodically. So my recommendation is you get this started, and then while it's running, you go on and you finish. And then basically, I want you to think about salt and what we talked about with sodium and chloride in the video that I made and posted for you already, and think about how the water molecules behave. And if the water is surrounding the sodium and chloride and interacting with it, then there will be fewer hydrogen bonds between the water molecules. And how will this impact melting rate? Will it make it slower? Will it make it faster? And why would disrupting hydrogen bonds make that difference? Then for activity 4, you get to have a little kitchen fun where basically you're looking to see what substances will dissolve in water and what substances will dissolve in oil. And so if you don't have, you know, 4 containers, and this is a typo, you're just using little containers, glasses, whatever it is, put a little bit of water in a couple, put a little bit of oil in a couple of them, and then basically in one of the water ones and one of the oil, you're going to mix in some sugar and see what happens. And in the other one with the water and the other one with oil, you're mixing in salt to see what happens. And then after you do that, you'll put some food coloring in. And I'm looking here, the food coloring is just kind of optional, right? And the food coloring might actually help you see better what is happening. And if you drop some food coloring in, you might be able to see, is it oil-based or water-based food coloring, and where does it go? Does it mix evenly? Can you tell where it dissolves or doesn't dissolve? And then based on that, you need to explain whether salt and sugar are charged or uncharged. And that basically means, are they polar or ionic or non-polar as far as the bonds within those 2 molecules. And then for activity 5, you're investigating how water molecules are attracted to each other, and basically how they are not only attracted to each other, but adhesion is how they stick to other polar or ionic surfaces. And so if you get the tableware knives together, think about how a knife could hold a charge, right? And so it could be attracted to water. And if you squish these 2 guys together and then you try to pull them apart a little bit, you should feel a little bit of suction. And what does that suction tell you? Well, it tells you about adhesion. And so this one, you don't have to actually draw anything, but you're just exploring it. And then for activity 6, you're going to have some fun floating things on the surface of water, and look at how soap might interrupt the ability of water to form hydrogen bonds with other water molecules. And so you need to draw what you find and then basically explain with hydrogen bonds why that pin is able to float on the surface of the water. And if you're struggling a little bit, go back and watch that Bozeman science video on the properties of water. It will really help. And look here, the last step that you do here is add some soap and see what happens. And then I believe this is the last activity, and I'm adding, if I haven't already, the file on pH, but watch the videos on pH and you'll see that water molecules can break up in just regular water, and so they ionize, and that's how you get OH or hydroxyl groups and H+. And when we measure pH, we're basically just measuring how much hydrogen there is. I really recommend you watch the video that I did with the board demo and see how it is that you count pH. And this website is just an interactive demo. You don't actually need pH paper. You're going to use this website to measure or simulate the pH of some materials. And so you'll be using a little pH probe in the simulation, and then you'll fill this information out, okay? And let me just show you, let's say if I have hydrochloric acid, but it is 0.1 molar, so it's a little bit diluted. I'm going to find that it has a pH of 1, and so my exponent would be 10 to the minus 1. And this is a little bit tricky. I have to tell it here when I'm drawing to make a superscript, okay? And then how would I write that? 0, well, what's 10 to the minus 1? Look at 10 to the minus 7. There's 6 zeros, and then the 1. So what's 10 to the minus 1 going to have? Well, if 7 is 6 zeros and a 1, then a 1 doesn't actually have any zeros, because that would be 0.1 right here for the hydrogen ion concentration. And that's how I get 10 to the minus 1, because it's 1 base 10 place removed from a value of 1. So you're going to fill this chart out and put this information in. And then for this one, pH 4 versus pH 2, remember, because it's a logarithmic or a base 10 system, then as we go lower in our pH value, then our acidity increases, meaning that the hydrogen ion concentration is greater. And how much higher? If you watch the video, for every step we have towards 0 on the pH chart from 0 to 14, we get a 10-fold increase. So if I go from 7 to 6 pH, then I have 10 times more hydrogen ions. If I go from 7 to 5, I jump 2 steps, 7 to 6 and 6 to 5. So 10 times 10, something that is a pH of 5 would have 100 times more hydrogen ions than something with a pH of 7. So I think that's enough information for you to figure out number 7. And I hope that this was helpful to you. I'm just going to look really quickly at our time here, and lecture assignment number 5 would be really helpful to you also, and that's why it's included, because it kind of walks you through considering what the pH of water and acids and bases are. And this is a little bit of a generality, and then you need to think about, based on what you've learned about acids and bases, this is telling you, hey, look, hydrogen ions, it's an acid. Hey, hydroxide ions, it's a base. Hey, why is this neutral? Well, if I count 1, 2, 3, 4, 5, 6 hydrogen ions, and 1, 2, 3, 4, 5, 6 hydroxide ions, well, 6 equals 6, and that's why this solution is neutral. So figure it out for this one. Is it an acid or a base or neutral? Look at this one. We know it's an acid. Look at this one. Why is it a base? Because even though this is NH4+, it's not free hydrogen, it's free hydroxyl groups, and that's what makes this a base. And then you need to go through and, hey, count the hydroxides and the hydrogens and figure out if this is an acid or a base, and how would you know? And then going through here, do you see how we have weakest, and then we have strongest on the right? As we get more and more dissociated or free hydrogen ions in the solution, then the acid becomes stronger. So the more hydrogen ions there are, the stronger it is. And if you look at it, hydrofluoric acid, HF, it doesn't fully ionize, and that's because the electronegativity differences between hydrogen and fluorine are actually right on the border between forming polar covalent bonds and forming ionic bonds. So occasionally the molecule ionizes and the hydrogen and the fluorine separate and become hydrogen and fluoride, and frequently it also remains covalently bonded together. And as I move to the right, I have the opportunity to see, oh, HCl, H2SO4, H3PO4, and so you can see that more and more hydrogen ions are able to dissociate and separate, okay? And this might be really helpful for you to go through before you try to answer the rest of the lab. And that is learning assignment number 4 and learning assignment number 5. And my Zoom meeting where you are invited for tomorrow from 3 to 4 is going to be about biological molecules. I hope you find this helpful, and I will post it as soon as I can get it to work.